Hello and welcome. My name is Patrick Tshala. I'm going to present to you binary numbers in this video, and this is part one. The content of this video is as displayed there, going through some background information, conversion, and BCD. As a human, or as humans, we are used to actually work with decimal numbers, and that consists of the digits 0 through to 9. However, computers and other digital systems understand mostly only binary numbers, which consists of ones and zeros. Let's have a look at the terminology. Binary number system is also called base 2. A base 2 number system uses binary digits. A binary digit is also called a bit, in short, and can be a 1 or a 0. A group of 8 bits is called a byte. A group of bytes is what makes a word. A group of 4 bits or half of a byte is called a nibble. Not much used nowadays, but it was really important at some point. Binary digits are joined together to form a binary numbers. Okay, examples I'm giving here. We have 1 0 0 0 1 0 1 0 1 0 0 1. So each of these is a good example of um, a number of binary digits that are joined together to form a number. In this screen here, we do have bits which are now grouped there um, on the top, showing the least significant bit, which is the rightmost bit, and the leftmost bit is called the most significant bit. At the bottom, we actually present or show how bytes and nibbles are represented. Understanding numbers and their values. Now, the position of the number, or actually the position of the digits are really important in order to calculate the value. And this applies to any number system. For decimal numbers, for example, starting from right to the left, the column weights are 1, 10, 100, 1000, and so on. So if we had a bigger number, the more left we were going, we have to multiply it by 10, as it is displayed here. This column here is a 1, ones column. That's tens column, hundreds column, thousands column, and so on. For binary numbers, we do have the columns here, which again from right to left, 1, 2, 4, and so on. Now, if we look at this one here, the way it goes is really, since we in this column we have 7 items, so we have 7 ones. We have 9 tens, which is there. We have 9 hundreds, and we have 1000. At the bottom is exactly the same thing, but that is the value of a binary number, always from right to left. Let's have a look at converting 10110 base 2. So we see the subscript here is saying that we are now working with a base 2 number. Now, We can actually use a table to help us. Use the table, use a chart, write the way you feel more comfortable. But I do like the tabular um, representation because it makes life much easier. We start by writing place values in the first row as we have here, which in fact we have 1, 2, 4, 8, 16. And these are coming from uh, those values in the brackets. Now, in the second row, we write the actual binary number we are going to convert. For each column, we multiply the number in the top row by the one in the bottom, or vice versa. The result will be exactly the same. So, for example, here, if I start from left, what I do is I basically multiply that to that, and so on. So I'll do that. That's what I have written at the bottom. So this one will give me the result that we have here. That's what I've written here, and the result is 22 uh, base 10, which is decimal. Pause the video and try converting some of the following unsigned binary numbers to decimal. Right, we can have a look at the answers now, and in brackets, in parentheses here, it is really explaining how we got those numbers. In this one, we have, remember the positions, that was 1, this is a 2, that is a 4, that one is a 8. So that is how we've actually come up with this value. And this principle applies to any of these. Double check it. If you have any issue, please drop me an email and I'll be happy to assist you. Now we are going to convert denary to binary. Now denary is just a posh way of saying decimal. There are two methods that can be used to do this conversion. One of them is sum of weights method, and the first bit produced from the operation is what actually constitutes the most significant bit. With the successive division method, the first bit that is actually produced from the operation is the least significant bit. Let's actually go and convert 47 decimal to binary using the sum of weights method. We start by creating a table, create a chart. You don't have to draw a table as such, but if you can actually put the place values in a thinking in a tabular way, that will make life much easier. So we write the place values as we remember. We have starting from right to left. We do have 1, 2, 4, and so on. We need to find the largest place value that is less or equal to 47. In this case, it should be 32. What we do is we write a 1 in that column. The column headed 32 is where we write the 1. And notice that that is now the most significant bit of our uh, binary number. What we do is we subtract 32 from 47, and the result is 15. We need to find the largest place value that is less or equal to 15, which is in this case 8. We write a 1 in the column headed 8. We subtract 8 from 15, we get 7. What we do is we try again to find the largest place value that is less or equal to 7. So we do exactly as we've done before. Um, we find the result is now, in this case, we have a 4, we write a 1, we subtract 4 from 7, the result is 3. We find, we try, so um, we try to find then, notice that from the very beginning, when we do subtraction, that is the value that will serve us in the next calculation. So what we do is we try to find the value that is, I mean, the largest place value that is less or equal to 3, which is 2. We write a 1, subtract 2 from 3, which is 1. We find the largest place value that is less or equal to 1. In this case, it's a 1. We write 1, which is in this case really the least significant bit. And then we fill the empty column with zeros. Pause the video and try converting some of the following decimal numbers to unsigned binary numbers. And in this case, we need to use the sum of weights method. Right. Take time to pause the video again to double check your answers. Are these correct? Or do you have something different? Any issue, please do contact me. I'll be happy to answer your request. Now, we are going to do the conversion again, but this time we use a method called successive division. We start off with a table, or we write, in fact, we don't start with a table as such, but what we want to do really is to have the place values. So we have 1, 2, 4, 8, and so on, as we've done before. Now, the way this works is that when we divide the number by the base, so the base in this case is 2, the remainder goes in the corresponding column. So this method is typically used for big numbers, but it really doesn't matter as long as it gives you the result that you want. We can actually start with 47 divided by 2, which is the base, equals 23 and half. Now the half is what we are interested in because that need to be time multiplied by 2, which is the base, to get the remainder in um, which is a base 2 now. Okay, we write that one there, and this gives us the least significant bit. We then move on. 23 divided by 2, which is 11 and a half. So the remainder is a 1 because remember once again what we have is really that we have the half. So 0.5 multiplied or times 2, which is the base, we have a 1 as we've done before. And then we write the 2 in the column headed 2. We repeat the same again. 11 divided by 2, which is a 5 with a remainder of 1. We write 1. 5 divided by 2, it's a 2 with a remainder of 1 in binary. Now remember that all the remainder, what we say, 1 is really binary. So is base 2. So converted from this operation there. We have 2 divided by 2, which is a 1. A remainder in this case is a 0. We write it down. 1 divided by 2 is a 0, which is half, 0.5. But then the remainder is a 1. Now, since the result is 0, always when you have a zero as a result, we stop the calculation. That is our binary displayed there. Pause the video, try converting these decimal numbers to unsigned binary numbers. Now in this case, we need to use successive division method to see how it works. Now pause the video again, check the result, and if everything looks correct, that's fine. Otherwise, please feel free to double check, or if there's something not that clear, please drop me an email. I'll be happy to come back to you. There is another coding mechanism, which is binary coded decimal. This is really simple method of representing decimal numbers in a binary form. So this is called a BCD, which is binary coded decimal. To convert a bit pattern in binary coded decimal, what you need to do is to group the bits into four and then convert each to a denary to a decimal digit as displayed here. Now this works both way. Um, Now in this case, really what we have is that on with this one, so that is the 4 bits in binary, and this is the 2 in decimal. So this number here, 8962, is in binary is that. And if we started with that one, converting it to decimal, then this is the way to go for it. Binary and hexadecimal numbers. Writing long binary can sometimes be really demanding, and often it will actually lead to error. There's a high probability of having errors when working with long binary numbers. Now, it's actually more convenient sometimes to work with a system which is a base 16. That system is called hexadecimal. Now, hexadecimal numbers use the digits 0 to 9 along with letters A to F. Now, column in base 10 have weights of 1, 16, 16 to the power of 2, and so on, exactly the same way as we've explained for others, but in this case the base is 16. That's why we use 16 there. The table here is showing you the hexadecimal digits and the equivalents in decimal. As we go from top to bottom, from 0 to 9, they are uh, they are the same. From 10 to 15, this is where it is different, because the hexadecimal will use the letters A to F, but in decimal we are actually uh, grouping these numbers together to give us the value as explained earlier in this video. The equivalent of this in binary is displayed. It's really useful to learn to produce this table without reading, and it's quite easy to produce anyway. You just increment, so each of these is really um, 0, 1, 2, we have there 2, 3, 4, and so on. It's really useful to practice and feel confident that you can produce it. Let's have a look at converting from binary binary to hexadecimal. Now we start and try to convert 111. So let's say we have 1111 010 and base 2 to hexadecimal. This conversion is easy. When we do a conversion between this binary and hexadecimal, we start reading from right, and then group of 4 bits are converted straight to binary to hexadecimal. So in this case, 1010 gives us an A in hexadecimal, and the next bits will be 111, which gives us a 7. So this is the result, 7A. Now pause the video, practice converting some of the following binary numbers to hexadecimal. Okay, now let's check the answers. Um, if you have everything there, that's fine. If you don't have the same answers, please double check. Or if you have any issue, please do contact me. I'll be happy to do that. Remember that we group this from left, 4, 4. So even with that one, remember we do, it's really 4, 4. Any of these must be grouped uh, in groups of 4 bits. Converting hexadecimal to binary. Now, when we do hexadecimal to binary number, we take 2ED base 16, and the conversion is really easy because the way it goes is that each hexadecimal digit directly corresponds to the 4 binary digits. That is how it works. So 2ED is straight away, as we can see, it really goes straight. So that is the result. The result here and that is the same, really. This one and that are really equal. Pause the video and try converting some of the following. Check the answers. Thank you for watching this video. Um, any feedback, any constructive feedback is always welcome. And please visit our website for more information, updates, and so on. Thank you. Je vous remercie. Kiitos. Tuossa kujila. Matondi mingi. Okay, bye.